Hello YouTube, this is Dr. Ronald W. Satz, founder and chair of the International Society of Unified Science and president of TransPower Corporation, a commercial and custom software manufacturing and certified systems engineering company. I work as a theoretical physicist and as a systems and mechanical engineer. Today's screencast, as with most of mine, is about the reciprocal system of theory. In previous screencasts, I've covered the entire macrocosmos, including all subjects you see on the right side here. This is the Microcosmos database main menu. I've covered the universe as a whole, galaxy clusters and groups, galaxies, star clusters, stars, planets, moons, minor bodies, nebulae, gas and dust, and voids. Now, here on the left side, let's go to the back here, to the Microcosmos database main menu. Up till today, I've covered solid matter properties, interatomic distance, valence, specific heat, energy and entropy, thermal expansion, compressibility, electrical and magnetic properties, isotopes, and I'm going to cover spectra today. In future screencasts, I'll be covering liquid vapor gas matter properties, cosmic elements and subatomic particle properties, and photon properties. So let's go to spectra. Top row is always the same in this database here. We have iron as the element. And by the way, this is only for atomic spectra. Nobody's worked out the molecular spectra in terms of the reciprocal system, although it shouldn't be too difficult to do, frankly. But I've done a great amount of work on the atomic spectra of every element. Here's iron, form number 1, atomic molecular weight is here, melting temperature, thermal factors, and compressibility factors. Of course, everything is quantized in the reciprocal system, including space and time. This slide here has to do with the work function and ionization energies. So here we go. The work function depends on the escape dimension of the rotational displacements of the atom, and specifically the speeds. So if we choose the magnetic dimension instead of the electric, by the way, these terms don't really have anything to do with charge in an ordinary atom. It's just that the magnetic is two-dimensional and the electric is one-dimensional. So we choose M, we choose the specific speed is 3 for this. And so we calculate a work function as 3.76. The observed value is 3.91. It's close enough. And then here I calculate the ionization energies in electron volts, which is like the work function. So stage 1, this is 2 times the work function, or 7.517. The observed value is 7.870. And then I calculate z minus 1 and z. And you can see it's pretty close, not exact, but pretty close. Now there are 2 slopes. Ionization energies have 2 segments. This is the slope of the first segment is given by the theory and then by best fit, and that's line 2. So this is the theory, that's the best fit to the observed values. Same thing with the second slope. And then here we have the individual levels of the ionization energy at each stage. Theory and then the best fit to the observed data. And here are the total values, which is summing everything before. And you can see it's a pretty close fit, not exact, but very close. Let's jump over to here. Photon properties. Now we want to know what photons are emitted when we do a transition. So here we have the Rydberg constant for the isotope, frequency in cycles per second, and the wave numbers in inverse centimeters here. We can either use the theory or the best fit. We'll use the theory. Best fit means the empirical data. And we can put in 2 atomic states here. And we're using ionization stage 2. And then we have N and M values for the atomic spectra calculation. So let's look at this tooltip here. Reciprocal system, time, space, region, thermal, translational quantum numbers for atom in state 1 and state 2. So these are the N and M values. And so we can get the temperature, we can get electron volts for the thermal energy of the atoms in state 1 and state 2. So there's a drop. See, there's a drop right there. So it's going to emit a photon. And then if there's magnetic or electric field applies only to state 2. That's if we were doing, well, that's right here. It's really 0. There's no issue here. Okay, so the frequency of the photon emitted, if we go from ionic stage 2 to 3, we get 2.17 times 10 to the 15th cycles per second. That's the energy of the resultant photon, 8.984 electron volts. That's the wavelength, and that's the wave number. And then there can be magnetic flux density. So if we had field splitting, we would get these splits in this. You can just see it's quite minor. It's very small. If there's resultant splitting photon frequency, wavelengths, and wave numbers from the electric field, if there's an electric field. There's no, I'm not using an electric field in this calculation, but if you, let's see, if you put an electric field up here, then you would get the splitting here. Okay, so now we can calculate the possible atomic states given the ionization stage and the observed photon wavelength. So if we observe a 10,000 angstrom photon coming out, what could have been the states of the atom? And, you know, here we go. So there's a tolerance function here, there's an N limit, so it's going to go up to 10 maximum for N and up to 30 maximum for M. And atomic state 1 is atomic state 2, so we're still in the same ionization stage in this particular calculation, but we're going from 3 and 7 for N and M to 7 and 13. So the calculated wavelength comes out to be 9,997.16, which is very close to the input 10,000. So this is most likely what happened. The atom had an N value of 3 and 7, and then it went to 7 and 13. And so it emitted this 9997.16 angstrom photon. And here maximum intensity line at the temperature. That's the temperature of the atom at which the maximum intensity is observed. So this is an observed value. The wave number is that, the line width is this, and then the intensity is calculated. It's complicated. The ergs per second, per centimeter squared, per hertz, per rad squared. So there it is there. And by the way, this is the default for doing this iteration on the n's and the m's. Okay, so that's a little complicated. You'll have to read the papers. So that's it for today. I'm going to just close this out so you can just look at the two main menus as I talk. The simplest possible treatment of the reciprocal system is my original work, The Unmysterious Universe, published many years ago but still in print. It has all the concepts, many diagrams. Again, it's the simplest treatment you can find anywhere about the reciprocal system. But if you do want all the mathematics, I mean all the mathematics, please obtain my magnum opus, Existence and Interactions, a computational treatise of the reciprocal system, the true theory of everything. 711 pages in the PDF file and 711 slides in the PowerPoint file. Thousands and thousands of equations, numerous tables, figures, drawings, everything. It'll take you months to go through it. And then when you're done with that, you would get these two database modules, Microcosmos database and the Macrocosmos database, and both these have excellent graphing routines included. My theoretical physics mentor, Dewey Larson, was also a theoretical economist, and I've made his work in theoretical economics also fully computational. That's in my Optimal Economist and Implementation of Larsonian Econophysics. The software program covers the economics and gives the econophysics equations for individuals, especially those if you want to plan for retirement, businesses and business sectors, and it also covers the macroeconomics of whole regions and countries. Totally supersedes Keynesian economics. There's a free paper you can find online. It's called Theory of Microeconomics and Macroeconomics, Larsonian Econophysics, by me. I suggest you read that if you really want to understand economics at a very deep level. It's way better than what you got in college. All right, well, that wraps it up for today. As usual, please study the reciprocal system and prove it for yourself. And thanks for your attention.